All right, so we just solved algebraically this equation. Let me put it in here. Let me put it in the third spot. So we solved uh, t plus 7 divided by t minus 2. And notice I'm putting in parentheses the numerator and the denominator, and then equals 5 over t, 5 divided by t, just to make it obvious what is in the numerator, what's in the denominator, what's attached, plus 3. So I solved this equation algebraically. So now what I want to do is use Desmos to help me check my answer. So I'm going to go ahead and graph this side. I'm going to call this f of t. And this is the rational functions typically have a value of x that they can't equal. Like in this case, if t equaled 2, that'd be a problem. If you look at our graph at t equals 2, on one side of the graph, one branch of this, it's going up to infinity on the right side of t equals 2. And on the left, if I were to actually type in t equals 2, equals 2, t equals 2. I just want, so I guess if I did x equals 2, let me do x equals 2. X equals 2. So you can see on either side of x equals 2, the graph goes up to positive infinity or down to negative infinity. That's how rational functions act around their asymptote. So this has a vertical asymptote at t equals 2. It also has a horizontal asymptote at y equals 1. So if I typed in y equals 1, you'll notice that over here it levels off at 1, and on the other direction it levels off at 1. That's another really common behavior in rational functions. So anyway, I want to graph this solution. So I have one function, f of t equals that. I'll put in another function, let's say g of t equals, and let's paste that there. Okay, and so this purple graph is this other one. What you'll notice is at either side of 0, it's going up to infinity and down to negative infinity. Also, this one doesn't level off at 1. This purple graph levels off at 3. Let me change this to 3. And the purple graph is leveling off at 3. There's a really good reason for why. I'm going to turn this one off here. I'll turn off x equals 2. Oh, if I made this x equals 0, which is the y-axis, you'll notice the purple graph approaches x equals 0, t equals 0. So let me turn this one off. So now I've graphed the left side in one equation. I graphed the right side in the other equation. And what I want to know is, when does the right side equal the left side? Well, they will equal each other when the graphs intersect. So let me find where these points where the graphs intersect. One is 5, 4, and one is -1, -2. Well, if you'll remember, we got t equals 5 and t equals -1 as our two solutions. Notice they are actual solutions. If either one were an extraneous solution, you would not have an intersection at that point. It wouldn't intersect because it's not really a solution. It's a solution for later on in the problem, but not to the original problem. It's not, the original graphs won't cross there. What about the 4? And what about the -2? Well, if I were to plug 5 in for t, this side would equal 4, and this side would equal 4. The value of t that makes that true is 5, though. So we say t equals 5 is the solution, and 4 is just what it makes either side. If I were to plug in -1, let me plug in -1. -1 plus 7 is 6. -1 minus 2 is is -3. So 6 over -3 is -2. Notice my y coordinate here is -2. If I plugged in -1 over here, we get 5 over -1 is -5 plus 3 is -2. So -2 is what it makes each side equal, but the value of t that makes each side equal to each other is -1 and 5. And this works for any equation that you would ever want to solve. You can solve them all graphically. You may not come up with an exact value, and maybe the problem asks you for the exact value. Maybe they cross at the square root of 2. Oof, and you have to give the exact value. Using Desmos could help, but Desmos's answer wouldn't be perfect for you until it gives exact radical expressions for their answers, and then maybe it would. All right, so that's how you can use Desmos to solve any equation, and we're using it to solve rational equations today.